Hello everybody. So what we're going to talk about today is a shorthand notation for writing down large and small numbers that you encounter in chemistry, which is called scientific notation. And then I'm going to talk a little bit about how measurements are made. And so you need to know the difference between exact and estimated measurements. And then finally, what I'm going to talk about is counting and operations using something called significant figures. And what you'll see is not all digits in a number or a measurement are considered important for a calculation. And so the ones that are important are called significant figures. The ones that are not important are not significant figures. Okay, so I'm going to now talk about scientific notation. So let me talk about what scientific notation is very good for. What it's great about is taking an extremely large number or an extremely small number and writing it in a very nice, handy shorthand form. So let me give you a couple examples of that. So the first example I have there is I have there that large number here that you see here, the number of atoms in 12 grams of carbon. So you can see that's an extremely large number there that we have. So if we were to write out that number in scientific notation, you would get this. 6.022 times 10 to the 23. So these two numbers, the large number and that number in scientific notation, are equivalent to one another. So one question you might ask yourself is, well, how do we take that large number and convert it into the scientific notation? And what we'll talk about and what I'll do examples of in a few minutes is you sort of know naturally that the decimal of the large number is there. And then in scientific notation, what you'll notice that the decimal has changed locations. It has gone out way out to here, so there's only one number to the left of it. And what we'll kind of demonstrate later is that you move the decimal over here in a large number to the left, and the number of times you move it over is the value of the exponent. So I would have moved that decimal 23 times, so the value of the exponent will be 23. Here's another way you might be able to think about it. So you notice in scientific notation, we have a number in front, you can call it a coefficient, and then times 10 with an exponent. So I'll write this number here, 6.022. Now let's say I multiply that number by 10. What number would that be? That would be 60.22. If I multiply by another 10, that would be 602.2. And if I multiply by another 10, that would be 6,022. So at this point, we are at 10, 10, 10, or 10 to the third power. So if I kept multiplying by tens, then I would eventually maybe get 23 tens. And when I've multiplied 6.022 by 10 to the 23rd power, in other words, 10 23 times, then I get that very large number there. Okay. Another thing that scientific notation is very good about is it's really good about providing a shorthand notation for very small numbers. And so we have an example of a small number there, which is a mass of a single carbon atom. So you can see that is, because of all those zeros in front, that is an extremely small number. And so I have that number there in scientific notation. Here, what I want to do is I would have a decimal there, and eventually I want to move it so that the decimal is right there, such that there's just one non-zero digit to the left of it. And so I'm going to move that decimal 1, 2, 3. So I'll move it 23 times again. But because this time I'm moving the decimal to the right, I indicate that with a negative exponent. So the number in scientific notation would be 1.99 times 10 to the negative 23. Another way you can think about this is, again, let's look at this number in scientific notation. Let's look at the coefficient here, 1.99. Now, if we were to multiply by 10, that would create a larger number, right? 19.9. Another 10 would be 199. But if we want to create this small number here, what you want to do is multiply it by tenths. So if you take 1.99 and multiply it by 1/10, that is 0.199. If you multiply by another tenth, or 1/100th, that would be 0.0199, and so on and so on. So if you were to multiply it by 23 of those 1/10ths, then you would get this small number here. The general form of the scientific notation is n times 10 to the m, where n is some number between 1 and 10. And so that is called the coefficient. M can be any kind of positive or negative integer. Okay, so let's practice some scientific notation really quick. So here we have a relatively large number in the sense that is larger than 1, and we want to convert it to scientific notation. So again, the goal in scientific notation is move the decimal place such that there's only one digit to the left of the decimal. So I'm going to move it 1, 2, 3 times. And so the new number, the coefficient is 1.4459. And since I move the decimal to the left 3 times, then the exponent will be positive 3. And again, it's positive because I moved the decimal to the left. With this number here, here is the decimal. I would move it 1, 2, 3, 4, 5, 6. So the number is 1.660780 times 10 to the 6. Okay, for the next number, you can see that's a very small number. So you might guess already that the exponent here would probably be negative. So we have the decimal is naturally there, and we're going to move it to the right. 1, 2, 3. So it's going to be 4.546 times 10 to the negative 3. And again, because we're moving the decimal place to the right, we're moving it 3 times now, the exponent will be the negative 3. Okay, so for the next number, let's count this out. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is what I get. And so it's going to be 4.2 times 10 to the negative 14 because it's negative because I'm moving that decimal place to the right. Okay, so how do you convert those numbers in scientific notation to a normal number? So if you were to do this, I first note, is the number a large number or a small number? So 2.58 times 10 to the 5 is a very large number. So we would want to create a number that is large. And so we just throw in a bunch of extra zeros here to the right. And then we move that decimal place 5 times to the right. So 1, 2, 3, 4, 5. So I get 258,000 is the normal number for 2.58 times 10 to the 5. For 3.42 times 10 to the negative 3, what we want to do is create a small number. So if that's the case, then we need to throw in some zeros to the left of those non-zero digits. So 0, 0, 0, 0, 0, 3, 4, 2. So in scientific notation, the decimal is between the 3 and the 4. And so this time, to create a small number, I have to move the decimal to the left 3 times. So it's 1, 2, 3. So the number I get is 0.00342. And so that number should be equivalent to 3.42 times 10 to the negative 3 in scientific notation. Okay, so you can learn some rules to add numbers in scientific notation or subtract them or multiply or divide them. Your calculator will do this for you, and the answer you get in the calculator will be correct. So I don't think you really need to know those rules, but if you're curious as to what those rules are, you can look at the slide that I have hidden in this presentation. Okay, so now what I want to do is talk about how measurements are made. And so what I want to mention a little bit about is the difference between something called an exact measurement versus something called an estimated measurement. So let me give you an example of an exact measurement. Let's say that you were counting the number of eggs in a carton of eggs. And let's say you open up the carton of eggs and all 12 eggs are there. And so you count them and you see that there are 12 eggs. And so one thing that you noticed is you knew exactly how many eggs were there. There were 12 eggs. There weren't 13 eggs or 8 eggs. And furthermore, you didn't have to make really an estimate as to the number of eggs were there. So for example, you weren't saying to yourself, well, looks like there may be 11.7 eggs. Well, I'm not so sure about that. Maybe 11.6 eggs or maybe 11.9 eggs. You didn't have to say that. So at no point when you're doing that count did you have to do an estimation of the number of things that were there. So when you don't have to make an estimation like that, that is an exact measurement. Another quick example would be the number of people in a class. You just count them, you know the exact number, and you don't have to estimate that there are 42.3 people or 42.5 people. You don't have to do that. You just count the people that are there, you know exactly what the number is. Now, when you're dealing with metric conversions, you'll get something like, for example, that there are 1,000 grams in a kilogram. That in itself is also an exact number. We know that there are exactly 1,000 grams in a kilogram, and we don't really have to estimate how many grams there are in a kilogram. So this will become a little bit more clear, but just kind of keep in the back of your mind, when we're dealing with exact numbers or measurements like the ones I just mentioned, these numbers are considered to have an infinite number of significant figures. That won't mean much now, but I'll talk about significant figures in a bit. So now compare that to estimated measurements, and let's see what the difference is. And so I think maybe a good way to explain how you make measurements that are estimated is, for example, let's measure the temperature of these two thermometers, A and B, and let's see what numbers we get, and maybe analyze a little bit the numbers we get. So if you look at thermometer A, what you can see here is that the temperature is definitely above 21 degrees Celsius, and it's definitely below 22 degrees Celsius. So one bit of information we know already with certainty is that the temperature is at least 21 degrees. And so what I'm going to do is just indicate that 21, those digits from thermometer A, those are certain digits. Now, at this point, what you can do if you wanted to is you can sort of subdivide the area between 21 and 22 into 10 equal spaces. Even though those markings, those 10 equal spaces are not there, what you can do is estimate the temperature with those 10 equal spaces to the nearest tenth of a degree. So it looks to me that I'm going to estimate, well, it looks like the temperature may be to 21.4 degrees Celsius. So this last number is estimated. So here we have a measurement with three numbers, and the first digits are certain, but the last digit is estimated. So this is an example of an estimated measurement. Okay, now let's look at thermometer B. Now with thermometer B, what you can see is that now you have not gradations every degree, we have gradations every tenth of a degree. And so one thing you can sort of see is that in thermometer B, the temperature is definitely between 21.4 and 21.5 degrees. So I'm going to write for thermometer B that we know for certain that it's at least 21.4 degrees. So these are the certain digits here. Now, again, what we can do is we can go out one more place. And so we can subdivide 21.4 up to 21.5 into 10 equal spaces so that we can measure out to a hundredths of a degree. And so I can estimate, again, one more place out. And so let's say I'm estimating, I'm making a guess, it could be 6, it could be 7, it could be 5. Let's just say I guess 5. And so here the temperature from thermometer B is 21.45 degrees Celsius. And so this last digit here is the estimated digit. Okay. Now you'll sort of notice there's a difference in how well we measure the temperature between thermometers A and B. So with thermometer A, we were able to estimate out to the tenths place. With thermometer B, because there were more gradations on the thermometer, we were able to estimate out to the hundredths place. So when you have a couple pieces of instrumentation and one allows you to measure out to further decimal places, it is said that that instrumentation is more precise. So it looks like thermometer B is the most precise in this case. Now, we have to sort of judge the quality of the digits by saying or asking, are these significant digits? Okay, so one of the things you'll learn is when you have a measurement and you have all non-zero digits, they're all considered to be significant digits. Also, when you have a measurement, all certain and estimated digits are considered significant. So with this first measurement here from thermometer A, we have 3 significant digits. And then with this thermometer B, these 4 digits, 3 again are certain, 1 is estimated. They're all significant. So with thermometer B, we received 4 significant figures. Okay, so the next thing we're going to cover now is we sort of understand when you're getting numbers from a measurement, many of them will be significant figures, but sometimes the digits in the number may not be considered significant figures, and so I have to sort of go over when do you know which digits in a number or measurement are significant and which digits are not. So let's go over those rules now. So the first rule is pretty easy to remember. So if you have a number or measurement and it all has non-zero digits, all non-zero digits are considered significant figures, and so with 1.234 kilograms, they're all non-zero digits, and so that should have 4 significant figures. If you have a 0 between non-zero digits, it's considered a significant figure, and so in that number there should be 3 significant figures. Now, zeros to the left of a non-zero digit, it doesn't matter if there's a decimal place there or not. If the zeros are to the left of a non-zero digit, they are not considered significant figures. So we have an 8 there, and those 2 zeros to the left of that, they are not considered significant figures. They are thought to be sort of placeholder zeros that put the 8 into the hundredths place. And so that number there, 0.08 liters, should only have 1 significant figure. If you have zeros to the right in a measurement or a number, and there is a decimal there, then all those zeros are considered to be significant figures. And so there we have 3 zeros to the right of the 1 and the 2, and so they would be considered significant. And so we should have 5 significant figures there. On the other hand, if you have zeros to the right of non-zero digits and there's no decimal, you should assume that those zeros are not significant. So in that number we have 239,000, but the zeros there are not significant because there's no decimal there. And so there should be only 3 significant figures there. So what does that mean? What that basically means is that our instrument can measure the difference between 239,000 or say 240,000 or 238,000. So the zeros there are merely placeholders that put the 9 into the thousands place. So I'm going to go through these numbers pretty quickly and indicate how many significant figures we have in each of these numbers. And also what I'm going to do is I'm going to put a bar over the number that is considered to be the uncertain digit. So the first number looks like we have all non-zero digits, and so we should have 4 significant figures. So we have 4 figures here, and the last number here of the significant figures is the estimated or uncertain digit, so I'm putting a bar over it. The next number, 3 significant figures. The next number, looks like we have a 0 there. However, the 0 is between non-zero digits, and so we should have 4 significant figures, and so the last significant figure is the estimated or uncertain digit. Now, with the next problem, all those zeros to the left of 911, you might remember that zeros to the left of non-zero digits, even if there's a decimal there, are not considered significant. So this has 3 significant figures, and the 1 there is the estimated digit. Next problem, those zeros to the left of 9 and 1 are not significant. The 0 on the right of 9 and 1 is significant because zeros on the right, and if there's a decimal there, they are considered significant. So this has 3 significant figures, and that last 0 is the estimated or uncertain digit. Now, with 1,000, you will notice that there is no decimal place in that number. The zeros are to the right of that non-zero digit, the 1 there. So in that case, those zeros are assumed not to be significant. So we really only have 1 significant figure there in 1,000 without the decimal. So there's only 1 significant figure here, and this 1 here is the uncertain digit. Now, as soon as you put a decimal place in the 1,000 there, all those zeros to the right of the 1 become significant. So we have 4 significant figures here. And now this 0 is an uncertain digit. So what is the difference between 1,000 without a decimal and 1,000 with a decimal? So the 1,000 without a decimal implies that you have a not so good instrument that can only measure out to the thousandths place accurately. So it could distinguish between 1,000 and 2,000 and 3,000. But when you have a 1,000 with a decimal, then you're implying that your instrument is more precise and that you can distinguish measurements at the ones place, say between 1,000 versus 1,001 versus 1,002 and 999. Okay, the next number down should have 7 significant figures. The last 0 is the uncertain digit. This has 4. I'm going to go a little bit quicker now. This has 2. This has 4. This has 4. This has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This has 6. This has 10. Now, when you have a number in scientific notation, that decimal, all those digits in the decimal are considered like regular numbers. So this has 2, and this has 2. Okay, moving on. So the next thing we're going to do is figure out how many significant figures an answer would have if you have measurements with different numbers of significant figures and you have to multiply or divide those measurements. So the basic rule to sort of think about here is, let's say we have 2 measurements. Let's say one is very precise, measured out to like the thousandths place. And let's say we have one that is not so precise. Let's say we have a measurement measured out to the ones place. Well, our answer can't be any more precise than the measurement with the least precision. So our answer probably would have to be rounded off to the ones place. That rule, which I just said, is going to be applied to these problems of multiplication and division. So the basic rule is this. When you have measurements that you're multiplying and dividing and you get an answer on your calculator, you round the answer on your calculator to the number of significant figures which is equivalent to the measurement with the least number of significant figures. So let's go ahead and try some problems. So with 1.23 times 45, there are 3 significant figures here, there are 2 here. Therefore, we have to round 5.35 to 2 significant figures. And so the uncertain digit here would be the 3 here. And so we look over to the right. If you're 5 or above, you round up. If you're 4, 3, 2, 1, or 0, you don't round up. So we are 5 or above. So to round this to 2 significant figures, the answer should be 5.4. Okay, the next one, we have 5 significant figures here. We have 2 here. And so what we want to do is round the answer to 2 significant figures. So this is the uncertain digit here. We have a 0 next to it, so we do not round up. So it's going to be 0.0056. Next one, we have 1 significant figure here. We have 4 here. We have 3 here. So what we want to do is round the answer to 1 significant figure. So I'm going to put a bar over the uncertain digit here, which is at 0.1. We look at the number next to it. It's above a 5. It's a 6. So we want to round up. So this should be 0.2. Okay, the next one, we have 3 significant figures. We have 4 significant figures here. We have 5 here. We have 5 here. So it looks like we want to round our answer to 3 significant figures. So it should be 0.652. Okay, moving on. Addition and subtraction has a completely different rule in that what you have to do is round your answer so that the answer's uncertain digit is in the same place as the measurement's uncertain digit that is furthest to the left. So let's go through a few problems so I can show you that. So if you look at 4510, I'm hoping you see that has 3 significant figures. And so this last 0 is not significant. The uncertain digit is in the tens place. With 978, there are 3 significant figures here. And so this uncertain digit is in the ones place. So what we want to do is round the answer so that its uncertain digit is at the place that is furthest to the left of the uncertain digits of the measurements. And so you can see that top measurement has an uncertain digit in the tens place, which is the furthest to the left. So we have to round the answer to the tens place. So this tens place should be the uncertain number. So it should be 5490 should be the answer. Okay, with the next problem, the uncertain digit in 250 is here. The uncertain digit in 0.098 is here. And so what we want to do is round the answer. So this uncertain number is to the furthest to the left of those two measurements. And so it's going to be in the tens place. So we want to round this to 250. Okay. Next problem. We have 4 significant figures in 4927. So the 7 is the uncertain digit. We have 3 significant figures in 73.4. So the 4 is an uncertain digit. And so what we want to do is round the answer such that the uncertain digit in the answer is the first to the left of the measurement. So we want to round that to the ones place. So what we want to do is round this to 4854. Okay, the next one, this is an uncertain digit here. This is an uncertain digit here. This is an uncertain digit here. So what we want to do is round this to the leftmost uncertain digit place. So we want to round this to the hundredths place. So we round this to 2700. Okay, uncertain digit here, uncertain digit here, uncertain digit here. Which one's the furthest to the left? It looks like the tenths place is the furthest to the left of those measurements. So we want to round 120.961 to the tenths place. So this is a little tricky. So if you take to the tenths place here, and you notice there's a 6 there, so we would have to round up 920, but we would have to change 120 to 121. So this is 121.0. So now the last thing I want to go over is what you do if you have an answer on your calculator that's in scientific notation and you have to round that number to correct number of significant figures. So first, we're going to look at the case where you are multiplying or dividing numbers in scientific notation. And again, you get an answer in scientific notation, you have to round it to the correct number of significant figures. So let's take a look at this example here on the left. And so what you can see is we have a top number here, which is 3.2600 times 10 to the negative 5. That's in scientific notation. And we're multiplying it by 1.78, which is a number that is not in scientific notation. And then on the calculator, you get this answer here in scientific notation. Now, this answer, it looks like to me there are 1, 2, 3, 4, 5 significant figures, but this is not rounded to the correct number of significant figures. So we have to do that. So how do we do that? So it doesn't matter whether you have numbers with exponents of 10 or not. You use the same rule that you used before for multiplication and division, where you round the decimal number in your answer to have as few significant figures as the measurement whose decimal number has the fewest significant figures. So let's look at this first number here, and what you can see is that there are 5 significant figures. Now, it says times 10 to the negative 5. That doesn't change anything. The number still has 5 significant figures, so I'm going to indicate that here. Then we're multiplying it by 1.78. You can see that this has 3 significant figures. Therefore, the answer decimal should be rounded to have only 3 significant figures. So here are the 3 significant figures, the 5 and the 8 and the 0. And then you might remember what you have to do is the uncertain digit is the 0. You have to look at the next number over and see if it's above 5. If it's above 5, then we increase the uncertain digit up 1. But you can see that here the number next to the uncertain digit, which appears to be in the thousandths place, is below 5. This number here, 2, is below 5. Therefore, we do not round up 5.80 to 5.81. Therefore, the answer should be 5.80 times 10 to the negative 5. And so this is the answer that you got in your calculator, but now it has the correct number of significant figures, which is 3. Okay, let's do the next problem. And so here we have 2 numbers in scientific notation, and you throw that into the calculator and you get this answer here in scientific notation. So the answer in the calculator is correct, but you have to round this to the correct number of significant figures. So let's go ahead and do that. So we look at the first measurement, and you can see that it looks like there are 5 significant figures here. Again, the power of 10 does not affect that. And then the next number here, you have 2 significant figures. Again, the power of 10 does not affect that. Therefore, we round the answer to have as many significant figures as the measurement with the fewest significant figures. So we need to round this answer to have 2 significant figures. And so here are the 2 figures that we want. And so what we're going to do is look at the number next to it and see if it's a 5 or above, and it is. So we need to round up 1.5 to 1.6. So the answer should be 1.6 times 10 to the negative 8. Okay, so now what I want to do is talk about the case where you're adding or subtracting numbers that are in scientific notation and taking the answer and rounding it to the correct number of significant figures. So let's look at this example here. And so here what we have is a situation where we have 3 different measurements. And what I want you to notice is that these 3 measurements have different powers of 10. So the first measurement is a number times 10 to the 5, the second measurement is a number times 10 to the 3, and the third measurement is a number times 10 to the 6. Now, if you were to add these numbers together, this is the number you would get on your calculator. So the number has 7 significant figures, and the exponent is times 10 to the 5. So the question is, how do you take this number with 7 significant figures and round it to the correct number of significant figures? So the rule for addition and subtraction of numbers in scientific notation is different than the rule you just learned about for multiplication and division. What you first have to do is to figure out the correct number of significant figures in the numbers you're adding or subtracting. What you have to do is take each of the measurements and convert it into an equivalent measurement where all 3 measurements have exactly the same power of 10. So what I've done is I've taken these 3 measurements here and I converted all 3 of them into equivalent numbers, but now they're all expressed in times 10 to the 5. So when we have 1.632 here times 10 to the 5, this is fine, this doesn't change. Now we have to convert 4.107 times 10 to the 3 into an equivalent number times 10 to the 5. And so the rule here is that when you are adding 1 unit to the exponent, then you move the decimal 1 place to the left. So we're going to, looks like we're going from times 10 to the 3 up to times 10 to the 5. So what we have to do is move this exponent 2 places to the left if we want it times 10 to the 5. So 4.107 times 10 to the 3 is 0.04107 times 10 to the 5. So that's fine. And then finally, we're going to take this number, which is 0.984 times 10 to the 6, and we're going to convert this to times 10 to the 5. And so we're reducing the power of 10 by 1. And so if you do that, then you move the decimal for every power of 10, you move it 1 over to the right. So we're going from 10 to the 6 to 10 to the 5. And so we have to move this decimal 1 to the right. And so 0.984 times 10 to the 6 is going to be equal to 9.84 times 10 to the 5. Now, once these numbers all have the same power of 10, then you can use the regular rule of addition and subtraction to figure out where you round your decimal answer to have the correct number of significant figures. So you might remember what that rule is. What you do is you notice in each of the measurements we're the last uncertain digit here. So in this first measurement, I'm marking the last uncertain digit, and it appears to be in the thousandth place. Here, the uncertain digit is, I think, in the 100,000th place. And then here in this measurement, the uncertain digit seems to be in the 100th place. And so you might remember that we notice which of these is furthest to the left. And it looks like it's going to be what? I'm going to just draw a line like this. And so you can see the one that's furthest to the left is the one in the 100th place. And so what we do is we round the answer so that its last digit is going to be in the 100th place. So it looks like it'll have 4 significant figures. Its last digit is in the 100th place. We look at the number next to it, and so we see that it's below 5. So we don't round 11.51 up to 11.52. It stays at 11.51. So it's going to be 11.51 times 10 to the 5. Okay, thank you for listening, and we'll see you next time.